So now that we've discussed a little bit in terms of circular orbits, a little bit in terms of elliptical orbits, I want us to talk about what the actual kind of physics are behind a satellite orbiting Earth. Not a satellite, really. Actually, I'm going to be doing the International Space Station as my example, although I know the image is an image of a satellite. The idea or the very concept of to be in orbit, and again, this is a bit of an oversimplification, but it would be this idea of constantly falling towards Earth, right? If I have the ISS, right, International Space Station, and it's above Earth, Earth, because of its mass, is going to pull it down via gravitational force. So let's write the equation for gravitational force. This is Fg, that's equal to gravitational constant derived from Newton. The big mass, or the mass of the first object, in this case, I'm going to call it big mass of the Earth, the mass of the space station divided by their radial distance squared, which just means the distance between their center masses. So we do have to include the radius of the Earth in that distance. And Earth's going to pull that satellite. So why do satellites not fall from the sky? Now, occasionally they do. Part of this has to do with the system is not quite this simple. It's a lot more complex than that. And then also people can make calculation errors. But in general, satellites don't fall. They do, however, move, but even in order to be stationary above a certain point. Have you ever wondered how a satellite does that? How does it stay stationary above a certain point? It is moving, and technically it's moving faster than we are, because it has to orbit us, it has to spin, it has to travel fast enough. So if I draw it this way, it has to travel fast enough this direction that by the time Earth pulls it down, it is matching Earth's speed in terms of rotation. It's falling with Earth as Earth spins, is the way you can think about it. And this is where we get this understanding of centripetal force. So something we haven't talked about yet. But centripetal force is equal to the mass of an object times the centripetal acceleration, which means the acceleration we get from changing direction. If you want to think, velocity and acceleration are both vectors. And I know you felt this when you're in a car. You don't really feel it if you're driving straight at about a constant speed. You kind of almost don't feel like you're in the car. What happens when you turn, especially if you turn fast? You feel it, right? Because velocity is a vector, acceleration is a vector. So even if I'm not changing how fast I'm going, just by changing my direction, I am creating acceleration. So another way we can reference this is it is equal to the mass, the velocity squared divided by the radial distance of the turn. So we won't get too much into the calculus where this is derived, but that's kind of the relationship between centripetal acceleration and centripetal force. Now, something I want to talk about, you'll probably have heard the term, maybe, centrifugal force. So this is the force you feel. It's technically, I don't like when people call it, it's not real, it's a fictitious force. Though technically that's kind of true. When I feel acceleration from a turn, I feel myself being pushed outward. The direction of the math for the force is actually pointed inward. So centripetal force is the actual force occurring. Centrifugal is kind of like the way we feel it. The best thing I want you to, or the best way I want you to understand this is they're just opposite directions. So the way we model centripetal force is opposite the direction we would feel it, is the way that we account for that in the math. The centripetal force, or in other words, will always point towards the center of the circle about which I'm turning, right? So if I'm in a car, this box is my car because I'm so great at drawing, and we're going to turn around, let's say we're turning around a corner, then the inside exterior of that corner, this is going to be pointing directly to where I'm going to feel I'm not going to feel it, but this is where the centripetal force would feel. And this is where I would feel the centrifugal force. Part of that is your body has inertia, and it takes a minute and it wants to resist the motion of the turn, so we feel it going out instead of going in. That's kind of the idea behind it. So that being said, I want to briefly talk about how this can relate to orbit of a satellite, right? So in terms of the satellite, Now, again, this is a little bit of an oversimplification, but the net force acting on the satellite is going to be the force of gravity. Now, if the satellite is moving, right, if it's not just stationary, because if it were just still and not moving at all in any direction, we'd expect it to fall towards Earth, which is what it would do, which does happen, right? In fact, actually, if anyone's ever seen, so we think meteors are so dangerous. A meteor shower is meteors hitting Earth. They're burning up in the atmosphere. So we get hit by meteors quite frequent. A lot of the time, actually, Jupiter is very good for us in terms of it takes the big meteors away. Most of the time, our atmosphere is enough to break them with friction and heat. But meteor showers are meteors coming and hitting Earth because they're hitting at just the right direction. They're not traveling, in this case, we could say left or right. But in this case, there's a gravitational force from Earth on the International Space Station. It is going to equal G of the gravitational constant. The mass of Earth, which I have listed above, I'm calling it ME. The mass of the International Space Station, which I'm going to call ISS, myths, and then the radial distance between the two. We'll call it R squared. The radial distance between these two is going to be, so HSS up here, that's the altitude height of the satellite from the surface of Earth. That's this distance right here. So this is HISS, altitude. And the radial distance is from the center of the Earth. This R has to include both. So this is Earth's radius. Now, Earth, again, you might have realized I mentioned earlier, Earth's not a perfect sphere. We're doing averages here. So this number that I've given you at 6,371 kilometers, that's an average radius. So R here is both of those. So we're going to just make it a little side note that R is equal to RE plus HISS, or HISS. That was unintentional, but slightly amusing. This has to equal, if I don't want it to fall, I want the satellite to stay in orbit. This needs to be perfectly equivalent to the centripetal force of the satellite. So this is going to equal the mass of the satellite, MISS, the velocity of the satellite squared, divided by, again, the same radial distance, where I get from the two equations. There's some terms that are equivalent here. I can cancel them out. Like, I don't even need to know what the mass of the satellite is. You'll notice I don't give it to us. And in this case, sorry, I keep saying satellite. I meant International Space Station. We could look up its mass, but it turns out it's actually completely irrelevant. It is solely dependent on its height and how fast it's going. So, or not its height, its altitude and how fast it's going. So how far away is it and how fast it's going. So I can cancel out some terms. I have the gravitational constant still. The mass of the Earth does matter. Over one of the R's will cancel, so I just have one of the radiuses, and this is going to equal the velocity of the space station squared. When I solve for the velocity of the space station, I get that it is equal to the square root gravitational constant mass of the Earth over the radial distance. We can plug in these to actually calculate them. Let's move that over here. I've got the square root of, we'll do 6.67 times 10 to the negative 11. I'm going to include the units, as you know I like to do, to make sure everything cancels. This is Newton meter squared per kilogram squared. This is then going to be multiplied by the mass of the Earth, which is 5.97 times 10 to the 24 kilograms. Big. As rightly so it should be. Way bigger than the space station. All of this divided by the radial distance, which I'm going to, this should all be under the square root. All under that square root. There we go. Which the radial distance is the combined radial distance. So this is going to be the radius of the Earth, which I'm going to have as 6,371 times 10 to the 3 meters, because it needs to be in meters, not kilometers. Few reasons. Newtons has meters in it. I want to make sure those cancel out properly. I'm also having the gravitational constant, which has meters in it as well. This plus the altitude, which is 400 times 10 to the 3 meters. And then we can calculate that. Let's look at, in terms of the newtons, I'm going to break up the newtons to show it's, a newton is a kilogram meter per second squared. I have a meter at the bottom, which can cancel with one of those meters at the top. 2 kilograms, so that's kilogram squared canceling with these kilograms squared. I'm left with meters squared per second squared, but it's under square root, so that's meters per second, which I'm looking for velocity. That's what I want to find. When we plug this into our calculator, we get that it is 7,668.7, we'll keep 2 decimal places, 3 meters per second, or we could write that as 7.67 kilometers per second. So we see it has to be going pretty fast. It has no relationship to its mass. It is really just how far away it is will relate to its speed in terms of how fast it's going.